Yeah, so thanks for everybody, both in person and online, and also thank you for coming to our event today. So let me introduce Or first. So Or is a senior research scientist at NVIDIA, and he is also an incoming assistant professor at the Tech-Can University. So he specialized in the fields of deep learning for 3D vision and geometry, also learning with reduced simulation. So today he is going to give a talk around the topic of data-driven simulation for AV.
All right. Yeah. All right. Thank you so much for the introduction. So yeah, it's exciting to be here. I have a lot of material prepared for you. So and it's getting hard, to rehearse a 1 hour talk. You need at least 1 hour, and it's getting harder to find those 1 hours. So bear with me. I have like a agenda planned, and I am planning to so it's more important that we enjoy this than we cover everything. But oh, so a second. Yeah, never mind. And I do have a plan. I'll hope to keep up with it, but I might have to skip a few slides. In any case, I'm happy to share the slides and take more conversations offline if there's anything that that I haven't covered and you guys are interested in. All right, so let's get started. Okay, so today I want to talk to you a little bit about some paradigm shift in simulation, right? This is like some part like a big agenda, right? And what is that big agenda? Traditional simulation mostly goes as follows, right? So why do we want simulation for driving in particular? Because the premise is that it can help us generate lots of training data, and some of it is hard to actually gather in real life, and that testing can be done in a controlled and safe environment. So we don't want to really risk any driver while putting the vehicle in like crazy situations. However, currently there are several like limitations that we see, right? One of them is that still simulation engines struggle to achieve full realism. The other is scale, right? So it's still very much a manual process to try and generate all those scenes. And as as last years have taught us, more data, better systems. So we need scale. And another issue is that we want to somehow, kind of like a sort of like I guess something that companies use a lot to train systems is to rely on logs recorded at driving and then replaying them. The problem with those logs, and they can capture essentially, if you recorded what you've driven, what you saw during a drive, you can replay that to the vehicle. The problem is you want to keep advancing your vehicle, and as you're going to make changes, that vehicle is going to maybe perform a little bit differently. Once it does, it deviates from the original video, and you can no longer use those log replays. So just to maybe that sounds trivial, but just to put it out there, like, why isn't this good enough to just collect data and just use it as a replay? So, we could think of a different way, right? We could imagine that idea of collecting data, but instead of just replaying it, we could think of it like, can we use the collected data and sort of turn this into assets in our simulator, right? So now we're borrowing this idea of a simulator, but we're just saying instead of like going through the manual process, we'll try to automate things as much as we can. So in a nutshell, what we're seeing here in the slide is exactly that, right? So we drive, we take cameras, we take LiDARs, everything that we can sense. If we need to like perform perception, all those capabilities that have been developed, use them, glean data from drives, and then repurpose this for a simulation. And the nice thing is that hopefully it helps bridge this realism gap, and that it can scale better, right? Because that was and we achieved that scale in diversity that doesn't require the manual effort. So that's the big picture. And how to get there, this is kind of like some sort of like a breakdown into chunks, right? On the way to get there, we need to take care of a few problems or a few challenges, right? So one of them is to reconstruct the scene. And by scene here, I mostly mean like the background, the thing that's mostly static. And that's reconstruction in appearance and geometry. And separately from that, we want to also reconstruct the assets. These are the things that would populate our scenes in our simulator. And on top, then we want to take these assets and we want to place them in the scene. So this is like what I call the augmented reality, but really what I mean is like we want a realistic insertion of objects into the scenes. And then, can you see, by the way, my cursor if I point here? Or
Yep.
perfect. So on top of just inserting the objects into the scene, we also need to move them around, and that we want to move them around in a realistic way, again, avoiding some manual labor in the process. And then finally, we don't want to do this only in camera. We want to do this in other sensors because cars use other sensors as well. So I don't have time to cover all of these topics, but we do kind of in the group sort of touch upon all of these different topics. So I will also touch upon them in the talk. I do plan to spend a little more time discussing these three hearts over here: the scene reconstruction, the motion estimation, and the sensor simulation. All right, so let's start with scene reconstruction. We've seen tremendous, improvement and advancements in neural field reconstruction. NERF is gonna come up a lot in my talk, and neural fields in general. And we sort of know how to take multi-cameras from a drive, clean up the scene from everything that moves in it, and reconstruct the static environment. What I want to dive a little bit more into is what do we do with the LiDAR point clouds, right? So I think we've seen a lot of work showing us that if we take the point clouds and we use them in the NERF reconstruction, we get improved appearance. But let's talk for a second about the surface itself. Why do we want surface reconstruction? So here, hopefully, this slide demonstrates the benefits of having surface reconstruction. First of all, it gives us the ability to use physics because we need to know where the drivable surface is. That helps us with object insertion because, for example, if you look at the moment here where the vehicle drives just behind the tree, you realize that to achieve that lighting effect, right, we need to know where the tree branches are masking the light. So this interaction between lighting of the scene, the shadow casting on the ground, all of that is achievable through our ability to reconstruct the scene surfaces, right? So physics, lighting, and all of that. Now, of course, this is by no means, sorry, a bug here, but this is by no means only for AV, right? So surface reconstruction is a long-standing problem in computer vision in general, and of course, scanning objects and being able to get a nice surface out of them is very useful for many applications, including putting them in some simulator. Again, we talked about light and intrinsic decomposition and shadow estimation are also useful applications. When we want to reconstruct surfaces from point clouds, we often face this, what I called here the generalization trade-off. And what do I mean by that? So let's kind of split general methods into three categories. We have the data-free category, which is, I don't know, like the Poisson reconstruction could be, I guess, the main representative of those, which we know respects the input points. Okay, that's essentially the only source of information it leverages, but it has no data gleaned priors, right? So it doesn't know what it's looking at. It only sees points, and it, to the best of its ability, tries to recover a surface that agrees with those points. Then, the 3D deep learning methods have brought us like very powerful feed-forward networks. But what those networks do, kind of in general, they take those points and they spit out a surface. Does this surface respect the input points? Well, hopefully, right? But we don't have a way to guarantee that. So a lot of times we'll see effects that are more akin to like retrieval than they are to reconstruction. So kind of like, if you will, the model pulls out of its memory the model that's, most closely resembles the input point clouds that it's currently looking at. And I guess to overcome this, some methods propose to, well, let's do this and then let's do test time optimization, a little bit. But these test time optimization techniques, they also suffer. First of all, they're slow, and then this is like a stochastic gradient descent optimization. So we don't have any guarantees on the converged solution. So here I'd like to propose a different approach to this, kind of try to sort of bring the best of all worlds, if you will. Hopefully I'll convince you. So let me introduce this idea of kernels and specifically learnable kernels, and we're gonna see how that can be useful to reconstruct surfaces. So first of all, I'm going to just, say that we're going to represent the surface as intrinsic, as implicit functions, neural fields, I should call them. And then what does the kernel method do? Well, basically the kernel method tells us that we can take any function, in this case, this is like a 1D illustration, and we can kind of write down this function as some weighted combination of kernel functions, right? And nothing learnable yet. I haven't said anything learnable. Once we agree on that, the only thing that's left to do is to say, if our basis functions, those kernel functions that can, that a weighted combination of them can represent any function, what's left to solve is how do we weight them? What are those alphas in this equation? What are those weights that we used in the composition that can recover the underlying function? The nice thing about this supports nicely a continuous representation like neural fields. We kind of discretize the problem. We shifted the problem into this discretized weights that we need to solve for. Now, here comes the learnable part. Nothing tells us that we have to commit to a set of prescribed kernels like Gaussians or splines or anything like that. We can actually try and learn those. And I'll show you how to do this. Here's just an illustration of an example of some kernels, some spatial visualization of how our kernels look like after they have been learned. Learned from what? Learned from trying to reconstruct a bunch of shapes that we show it. So what we're going to do, and hopefully this is not too scary, but I haven't wrote anything like different here. I just said, like, again, the function, the continuous function I want to represent is some weighted combination of kernel functions. Only notice that I added this theta here to say that my kernel is now a learnable function. So it's not only a function of the input coordinate or pairs of coordinates x and z, it's also some feature that I can learn in those coordinates. Okay, and here in particular, this is from a work called neural kernel fields. So the kernel we used in this work is this neural splines, but this is not like I mean, again, the choice of kernel here is kind of flexible. All right, so what's going on here? How do we achieve those learnable kernels? Basically, we take our input point cloud, we put it through some network that processes the points here using a dense grid. We'll talk about that later. That grid lets us interpolate. That grid predicts like we predict feature points in grid corners, as more like recent neural fields methods do, and then lets us query any point in a continuous space and query its feature. Once we have those features, we can go and say, basically, now we want to learn how to solve this weights, right? These weights alpha. How do we weight those kernels? So we need to first solve the inverse solve of the kernel, the ridge regression problem. To do that, we need to establish kind of this matrix, which basically says take any pair of points, like on my support points. These are the points on the shape itself, and near those support points, I just want to supervise them with is this region occupied or not occupied? So my labels here are whether this is occupied or not. This could also be the assigned distance field if I have that information. This is up to a choice. So here I'm kind of writing them as like features at xi, xj, where xi, xj are points, but really what I'm doing is like shifting every point a little bit outwards and inwards from the surface, because then I can control whether my label is occupied or not occupied regions. And then basically what I'm doing is my test time optimization became just this linear solve. So I'm converging in one step solve to one optimal solution to recover my weights. I'm training my feature extraction problem, my feature extraction network on many such synthetic objects, which basically transfer the learning. I'm gleaning priors into my networks, but I'm not done. The problem will only be solved after I do this test time optimization through linear solve. So this is why I'm saying I'm kind of bridging these both these ideas of feed-forward networks and test time optimization, but making it fast and more robust, right? So with those recovered weights, I can go back and sample any points that I want in the 3D space, and basically get the function value at that point. So now I have my full, like I have my full spatial kind of occupancy representation of the shape that I can now extract a mesh from. So this is kind of the basic idea of this work. Now, the nice thing is that we keep this idea of having data-driven priors, but instead of a full feed forward, we shifted to this test time optimization, and then we're guaranteed to get a global optimum. And here I'm showing some examples of how this pays off, right? So for example, you see that without any like more powerful network than, for example, what's used in occupancy networks, by just respecting the input points more, we can recover those more fine details on the boat here, right? And yeah. And yeah, if we I don't want to go into like how do we do this completion, because this like steers me away a little bit from the story. I'll talk about that later. All right, so yeah, so I think the main power of this method is, again, this generalization ability. So what I think is most exciting to see that we got here is this, or maybe I can zoom, I can go back for 1 second and say that in practice, anyone that you talk to that works on practical reconstruction problem, they all end up opting to use Poisson reconstruction. And that kind of bothers us, right? So we say, how come we've done so much progress in 3D learning, and so many like papers show us beautiful reconstruction of surfaces, but then no one actually goes and uses them. And I think that's one of the problems, that in real world settings, there's noise. And there's you want to generalize. You can't just train on chairs and then go to an entire scene and hope that it works out of the box. So I think that's kind of like the core idea, and this is what I'm showing here. That first of all, yes, we do get in category reconstruction that's impressive, but I think what's nicer to see here is that if I train on chairs, for example, and then I go and test it on whatever, like cars and boats and airplanes, I still can recover state-of-the-art results without ever seeing those, which I think kind of stands for this idea of respecting the points at test time. So man-made objects like chairs, they tell us a lot about local geometry and how to reconstruct it. If we can take those priors, they should be transferable to other categories. And that's the main idea. And the other generalization aspect of this, what I'm showing here in the middle, is some generalization to the point density. So again, a lot of feed-forward networks, they kind of they're trained on a specific number of sampled points, and then they can only once you introduce more points, they don't work better. That's a property, again, Poisson reconstruction would not do that. It would maybe fail if you show it like too sparse of an input point cloud. But the more you go and densify the point cloud, you'll actually improve your results. And that's the behavior that you want to see from a test time optimization network. And that's something that we are able to achieve here. And here on the right, I'm showing like some examples of scaling this up to scenes. Now, there is a problem here, right? And the problem is exactly this: scale and noise. So noise I haven't talked about, but 1 second. Scale suffers because we reconstruct this dense, first of all, this dense network, and second of which the dense, our linear solve needs to work on like this dense matrix that we've seen. So yes, global optimum, but takes a long time to solve. That doesn't solve the problem, right? So here I want to share like our CVPR paper that touches exactly on those limitations of neural kernel fields. So the main goals of this work is basically to take this idea of neural kernel fields and basically scale them to hopefully one day be a good candidate to have people stop using Poisson and start using our technique. Not that I have anything against Poisson reconstruction, just want to make a dent in the world. So okay, so here are some examples of hopefully convincingly scalable or like large point cloud inputs that we've processed in one go in using this technique in a comparison to baseline. And again, the emphasis is going to be on like robustness to noise and scale. Okay, so how do we handle scalability? Well, a few things here. First of all, let me check how I'm doing on time. Bit behind. Okay, we'll be fine. First of all, how do we handle scale? So one key element in making this thing scale is to make the is to not use a global support kernel function. In the previous work, we've used global support. I haven't shown you the function itself, what it looks like. The visualization is a bit tricky, but basically any point in space would interact with any point on the surface. And that's good on the one hand, because it allows us to do this kind of completion in empty space, if we train on the right categories. But because the support is global, we can't chunk and we can sparsify the linear solve into regions. So a very simple idea would be to say, okay, let's stop using those global support kernels. Let's only solve the local problem. We can easily do this by a weighted window on top of our learnable kernels, and we just make sure that it shuts it down after a certain distance. And that would sparsify our linear solve problem and immediately would scale. The other idea is to use hierarchy. But 1 second before that, is to use hierarchy. So what we're going to do is we're not going to at one go use a dense a grid that computes the network, or I guess again everywhere in a dense fashion in volume, but instead we have the network predict to itself where it wants to focus its energy. So we're not going to populate all the voxels. We're going to have a hierarchy of voxels, and the course level will predict where it wants to mask out, say like this region is not gonna have any surfaces in it, and where it wants to focus more and split it down further into a lower or higher resolution. So one more step in the hierarchy. And then I haven't talked about, I just kind of mentioned before that neural kernel fields suffer from noise robustness because it doesn't have any explicit way to handle noise. We did introduce some weighting scheme, but that helped only for small amounts of noise. Here, what we found is that if we can actually introduce not just trying to minimize the function value on the surface, but also try to minimize that the gradient of the function agrees with some predicted normal, then that really helps battle larger levels of noise. And that's really key to make this thing work. I'll briefly mention a little bit more of that. So hopefully this diagram now is going to be much simpler to understand, because I've already showed you like the dense version of it. So this is going to be just the sparse version of the same thing. So again, we're going to process the input point cloud, but this time we're going to populate this hierarchy of grid. This is not a dense grid anymore, but nothing changed in the fact that I can still query a continuous coordinate and ask for the features. Only this time the feature is going to be, where did I have that? Oh, right here. The feature is going to be a hierarchy. So you see like every level of the hierarchy has its own weighted combination of kernel functions. So same thing goes here. Now from the bottleneck layer of that network happens this hierarchy prediction. So it's going to say, well, I start with some kind of bounding box that I'm going to decide at first on some grid resolution, and then I'll take my input point cloud and I'm going to just, break down this this bounding box into the sparsest, so into the coarsest level of voxels. But then I'll have this classification layer that tells me which one do I want to further go and split and which one I want to shut down. And then this helps us to turn this dense linear solve into a sparse linear solve. And now we have sparse linear system. We have a sparse linear system. We have very fast sparse linear solvers that we can leverage. So everything scales much more nicely. Okay. Really briefly, as I said, there's a lot of things that help this work. I think one key element that really is important here is to have this normal loss over function gradients. This element here is kind of key to make this thing work. It's slightly different in the sense that now what we're doing essentially is we let the network predict the normal inside voxel centers instead of on the corner, or instead of on the surface points. And then we can supervise, but we can query it anywhere, and we can supervise that the gradient of our function agrees with the normal on the surface points. So if this was a bit too fast, we can go in questions later. And then our masking model helps us avoid these situations where like Poisson likes to nicely complete the minimal surface kind of reconstruction that tends to blow up whenever you don't have any points behind your surface. So our masking model helps avoid that. Now, I should also mention that we have this prediction of the mask happens from another MLP that goes on top of the learned features. Nothing prevents us from using that for other purposes, like predicting texture or predicting inlier and avoiding additional noise. So I think the cool thing about this is this one really scales. I see like the verification on Twitter. Yeah, so the key thing is basically that now we have this ability to train on multiple data sets at once. So I think that's really key here, that we have one model that kind of is sort of like, we call it like the kitchen sink model, right? So this is kind of like it's aimed at serving it just being an out-of-the-box solution. That's the thing we were missing before, that we said we don't want to train on chairs and evaluate on chairs. We also don't want to train on chairs and evaluate on airplanes. We actually want to train on everything that's available to us in synthetic world, and then go and just hopefully make it work on the outside world. So here are some examples of how it works on this is Thingy 10K. This is object level. Let me show you quickly some results on. So this is trained on Carla. We actually like prepared some kind of like a data set from Carla, which is large scale enough. And then we took this and we tried it on Waymo. So we've never seen like real AV data before. Still, we were able to like recover pretty decent kind of reconstructions on Waymo. Let me show you this video here. I think that will be kind of, oh, this is still the Carla, right? Just to show kind of scale, right? So this is done in one go, and I think this is the power of this kind of the hierarchy and the efficient solver. And this is when we take it to Waymo, and we can actually see that it's transfers pretty nicely. Now you see this SPSR. This is kind of exactly those blow-ups that I was talking about earlier that now we're able to avoid. So there's going to be like a comparison here. You see how the back of this sign, because we could predict that there's no surface there, we could penalize this region. Whereas if you don't have that information, you just complete the minimal kind of surface and it will blow up. And processing time is fast. Second. And this is just a fun like racetrack example that we got like millions of points, and it was trained like under 2 minutes. This whole racetrack was just trained. Let me show you this with the texture on it. As I said, like we have this head that can predict texture. So this is fun. Cool. So hopefully, this was, I don't know, this was a bit quick, but hopefully this was a convincing argument that we're on the right path, or I feel like we're this is my agenda, right? I think this kernel methods are really powerful, and what I'm trying here to do is to convince you that it brings like the best of both worlds. You can do some learning of data priors and test time optimization. And if you're smart about scale and noise, then you can actually make this useful in real world application.
Or can I ask a quick question?
Yeah, of course.
I remember at the beginning of this part of the talk, you motivated this by talking about all these neural field models and how you can extract surfaces from them, and that these do better when you include points. And then all of this work has been, as far as I can tell that you've been talking about, has been reconstruction just with points. So is there, like, do you have something that you've done or something in the works where you're going to combine both the point cloud and all the imagery you get to sort of do even better? Is that something that's happening? Or
yeah, that's a fantastic question. We actually have like I'm not talking about this today, but we can, happy to talk about this later. We have a CVPR submission that does not reconstruction from point cloud, but reconstruction from images, that does like basically a fusion algorithm from images into surface that accounts for the image semantics. So we're seeing like all those like amazing semantic networks, and self-supervised features, and like LSEG and segment anything and all of those popping out. So yeah, so I think your question is spot on. Like, why don't we use all that important information? I think nowadays we kind of, semantics in 3D comes after you have the 3D. And I guess like a core question is like, can we actually leverage semantics as we reconstruct the 3D? If I get your question. And,
yeah, well, or even just, not even if you're doing semantics, but just like, the points, even if you have pretty dense points, you could still get, presumably the sensor package that gathered those also had RGB cameras on them. And if you were using that data as well. I mean, I assume you must be using it to some extent because of the texture prediction that you did. But I mean, if you're at the end of the day, if you're like you have this neural feature field, right, that you then you interpolate with these kernels, it seems like that multi-view imagery could really inform what goes into that feature field in addition to the points. Yeah.
Yeah, I fully agree, and yeah, and I agree. Like, you know, bundle fusion methods, they only use the color in a way, right?
Right.
And these methods only use the point clouds, and the, you know, you like ideally want to marry those two ideas, right?
Yeah.
Mm-hmm.
Cool.
Yeah, yeah, I shared, yeah, I'll share it in the last slide. There's like some reading list, so I you know, there is some pointer to the, oh, sorry, it's not online yet. Yeah, I can share, I can just send it to you.
Cool.
It's yeah, it's coming up on CVPR. So okay, so because I'm really late on my plan, I'm gonna really quickly just mention a few things here about like object reconstruction, augmented reality. So basically, all I'm trying to say here is that, you know, objects are out there, and instead of trying to come up with like synthetic objects, we should harvest them from scenes, and then we can another alternative to do that, or some complementary stage, is to actually generate them. And I think the probably some middle point is the right answer. So, you know, some observations along with some generation would be the ideal. Here I'm just pointing you to two works that came out from our group about like generation of 3D assets that can learn already from images or from point clouds. And again, considering the last question, we probably should consider both simultaneously. And this is how we can insert those objects into the scene, you know, using physics and using lighting estimation. So again, not gonna go into details around that. Okay, moving on to talking about motion. There's two types of like, or two main categories that we care about. We care about how to move vehicles, and we care about how to move humans. That's mostly, right? Then I think other things will, you know, we could pay attention to other things later. This is just kind of you know, to briefly mention, kind of, this is a work where we learned a motion model that helped us recover real recorded drives and put them in a simulator. So here we didn't, this is not the neural simulator, this is a traditional simulator. But the automation we've done is, you know, instead of manually instructing the vehicles to drive, we glean those drives, those trajectories from real drives, and we place them in the simulator. And what this lets us do is it lets us manipulate them and create, for example, these kind of collision scenarios that weren't otherwise available to us, or if they were, probably scarce and not safe. So this way we could actually you know, manipulate towards achieving adversarial scenarios. So just not going to go into the details, but basically we've learned a motion model from a lot of drives, and then we manipulated that motion model using test time control to achieve some desired goals. For example, have another agent collide with the agent you optimize for. And in this scheme, we also like have a black box planner in the loop that, together with the optimization of the collision, makes sure that the actions that the ego agent is trying to do are passed through a planner. So you can work together with any black box planner. It doesn't have to be differentiable. I do want to mention a little bit more in more details what do we do with humans. So this is again a recent work that came out that's going to be shown at CVPR, and here we focus on human motion modeling. Now we've split this motion modeling into two parts. One we call trace, this is the trajectory prediction, and one we call pacer. So this pacer is an RL-based method that takes the planned trajectories and tries to follow the waypoints to the best of its ability while accounting for its environment. Key point in this work, let me play the video while I'm talking. Key point in this talk, in this work, is controllability. That's the main thing that we're striving to achieve, right? We want to have this kind of baseline motion model, something that can generate anything, but then we want the ability to just control it, guide it towards any task that we need to that we're going to face. We don't want to pre-train directly for one task. And in this work, we've done controllability towards several things like waypoint goals, collision avoidance, and walking in social groups. So the base model is based on a diffusion model that that's conditioned on both the map and other agent trajectory history. Together, those two are, they're conditioning the future prediction trajectory of the agent. Now, guidance comes only at test time, so we don't train with guidance aside for these conditions. And what this lets us do is, we can, for example, based on this map, for example, most agents would commit to staying on the sidewalk, which is safer for them. Okay, so this is what will come from condition. But if we want them to go to a certain goal, we can actually force them to go into a certain goal or follow some social behavior. Now, we have a lot of ways to introduce controllability into this. One of them actually already comes in the condition. For example, if you take driving data, if you take pedestrian trajectories from driving data, they come with semantic maps that tells you where is the walkable region. What that would cause is that if you only train on this data, your agents would always commit to walking on the sidewalk because there are hardly ever examples of pedestrians getting off the sidewalk. Now, that's a problem, right? Because what if we did want to generate like a scenario where a pedestrian jumps to the street? Well, in this case, we could look at other data sets where we see pedestrians not in a different environment, not in a driving environment. The problem is there we don't have any map or semantic map of the walkable region. So a method like classifier-free methods allows us to drop that guidance, that condition, and then train with both. And the nice thing is that at test time we can control. We have this knob to control how much we want to account for the map if we wanted to. So now we basically train on two populations of data, one that has maps, one that doesn't have map. The one that doesn't have map can get us, the way people walk in social groups or in random direct or in, whatever directions. Like this one was taken from, for example, students walking campus. And then if you merge the two, you can actually say, okay, now I want them to walk on the sidewalk, but sometimes less so. So I have this knob to control the guidance. Now, other test time guidance comes actually because the diffusion model lets us introduce in the denoising process, they let us introduce additional rewards or penalties. And this is a very powerful idea because as we denoise the noise, so we start with a noisy trajectory here. I'm not really showing the process, but we start with a noisy trajectory and then we denoise it, right? Much like diffusion models work in images, we denoise it towards the final clean trajectory. If we add this guidance in the form of, for example, collision avoidance, meaning at every point we will model our agent as some as some sphere, and then all the other agents as other spheres, and we have a differentiable way now to compute the collision, we can actually propagate that penalty into the denoising process. And at every denoising step, make sure that we're colliding less and less, right? So this guidance would work at test time until we get a collision-free trajectory. Key here is to do that guidance on the clean prediction. So this is something that we've seen to work like much better, because if you try to compute collision on an intermediate noisy result, right? I think intuitively it kind of makes sense. Then you realize that you get so many noisy rewards. It makes much more sense to early on predict your from the noisy state, predict already all the way through to the clean trajectory. That's not going to be a very refined trajectory, but actually that's pretty good, because on this average trajectory, that's a good idea to start plugging in those rewards on avoiding collisions. So this would be collisions with agents. We also have a scheme to do collisions with obstacles, which try to minimize the overlap here between we kind of grid sample the points on the agent and on the obstacle, and we try to push them away from each other while stopping the gradients on the obstacle. And then there's the kind of follow the leader sort of social group. So actually, like if you look at the appendix of this work, it's full of like really nice ideas we had on all sorts of kind of guidance that you can introduce at test time. Essentially, anything you can write down as a differentiable function, you can use. So you can use to guide your trajectory into a certain waypoint, and that waypoint could even be further away from the future that the trajectory is planned for. So if you plan for 5 seconds and you want a target goal that's like 30 seconds away, it's fine, because with an autoregressive model, you can do that. I just need to make sure that you somehow preserve some minimization of distance towards your final goal. So a lot of tricks. I really invite you to dig deep into that part. I think one specifically cool trick here is that, remember, we have the spacer. That's the RL-based model. That is the model that actually accounts for very local interactions, like avoiding, like for example, that's the only way you could achieve like a refined maneuver to, like, you know, if you come across another person in like a sidewalk and you just want to shift just a scooch over just a tiny bit to avoid collision. That's something that would come from the RL engine, from the animation that's aware of the body dimensions and everything to a high resolution. That thing has a learnable value function that it tries to minimize. So a cool trick you could do, and that's what we've done here, is we can actually take this value function, and it's differentiable, so we can use that value function as one of the penalties we introduce in the tracer. So already the trajectory planner is accounting for the value function that the pacer is going to, that the RL model is going to use, trying to make it, you know, as the reward as large as possible. Hopefully that was sort of clear. Let me show you some examples. So this is what pacer does. Yeah, this is exactly kind of this kind of awkward, you know, two people trying to not bump into each other scenario where the RL agent can try to fix that. This is like a full system of crowd simulation, just kind of throw a bunch of them in there and have them try to avoid, you know, hitting each other. And this is the social group. So we've marked here kind of who should walk together, right? And there's a leader, the leader has a goal, and the other's goal is to stay kind of close to some group member. So they kind of walk jointly in groups. So the nice thing about this, like, for example, we didn't use a data set that had social groups marked in them. We didn't have that annotated, right? That's a reward you can introduce at test time if you can imagine as a mathematical function or differentiable function how people walk together, right? So it will only be as natural as our math could model here in a way. But you know, if we could learn this from actually annotated data, we could use that as a reward as well. More of a demonstration of what could be done. And the nice thing about using this RL-based method, it can now accommodate to other terrains as well. So it actually works with a height map. Our trajectory is not planned using a height map. It just uses the semantic map. But the RL agent is trying to actually implement that waypoints. And if there's a slope, it should account for that slope. Okay, skipping forward. This is maybe just one more where we just dress them up. Nothing fancy here. We just took these humanoids and dressed them up and kind of demonstrated this, you know, starts to look like something that, you know, could be fun to populate an actual urban scene with. Okay. I don't have much time left. 15 minutes. Yeah, that should be fine. That should be fine. Okay. Any questions on that?
I have a minor thing, but in the interest of time, I'll let you keep going.
Got it. All right. Then I'll keep going and we can talk about that later. Okay, so the final kind of part of my talk, I wanna share something that we're kind of a little bit of an ongoing work, but towards completion. This is trying to take neural fields and use them to do novel view synthesis, but this time of LiDAR instead of camera views. Again, and this is joint work with colleagues from ETH. So it's Konrad Schindler and Shengi, who was an intern with us, who did a fantastic job. Okay, so you know, NERF is great, right? Why is it great at generating novel views? I'd argue that, you know, a critical point here is that it's optimized for that task exactly, right? It's not optimized for reconstructing the best underlying surface. It's optimized for reconstructing the view that you want it to generate. It does this by breaking down the representation of the scene and modeling the interaction of the sensor with the scene. This is the sensing process through volumetric rendering, right? How do we take these principles and we take them from cameras and transfer them into LiDAR, right? So currently it's tailored to camera views, but we like the underlying principle. And this is the premise of this work. Quick motivation, why do we want to do this? Again, for the same reason that I've been saying all along. We don't want to redrive with every sensor configuration possible and collect all the data from everywhere, right? That doesn't make sense. We'd want to drive once, collect the LiDAR scans, and then repurpose those scans to what would have happened if I drove on the next lane? What would happen if I, turn my LiDAR downwards a little bit, or change its number of beams, right? So this LiDAR configuration and installation points and even the trajectory of the vehicle may vary, and we want to, again, reutilize what we've recorded into novel scenarios. Now, how was this done before? Using this two-step procedure. First, you drive, then you take your points, you reconstruct the surface from them, and then hopefully you can take those surfaces with some learned features and learn a function that maps them to what the LiDAR would see. And just a quick reminder, like 2 slides ago, I was saying that I think NERF is great at its job because it directly optimizes for the task of novel view synthesis. And here I'm, and what bothers me with this method, which is fantastic, by the way, is that it doesn't, like the first step of the surface reconstruction is completely agnostic to what you're going to do with the surface later on, right? Because it doesn't know you want to render LiDAR from it, right? So if you have errors in the reconstruction phase, they're gonna propagate to errors in the LiDAR modeling phase. Now, it's not entirely novel to try and take NERF or neural field representation and try to do other stuff with them by novel view synthesis. I'll just kind of, to put this in context, there have been works trying to take depth into consideration, but they're mostly purposed at aiding the visual, the appearance reconstruction, not at modeling the best LiDAR reconstruction. And therefore, like, they're kind of treat depth as ground truth, as correct. Okay, they're not trying to look at the LiDAR properties, which I'll introduce in a second. We talked about surface reconstruction, so clearly that's another use case of neural fields, very powerful. And I guess more closely to what I'm trying to show here is works that try to model unique sensors, like the time of flight sensor or the event camera, that kind of try to account for the sensing interaction with the scene. So our work kind of falls more into that bucket. So what's a LiDAR? What let's start with that maybe. A LiDAR is something that shoots a laser into the scene. That beam hits a surface and it's returned to the sensor. If enough energy was returned, we can count the time that passed between the moment we shot it and the moment we got it back. And if it pressed some threshold, if enough energy came back, we can take that time, multiply it by the speed of light, and say what the range of that surface is. Okay. If you look at actual LiDAR range maps from LiDAR, we'll see that often there's a, depending on the sensor, of course, there's a single return, which is the use case I was just describing. But there's a lot of times you'll see 2 returns, right? And these 2 returns are actually, that's a property of a LiDAR that we want to be able to reproduce in our model. We don't just to ignore them. Maybe, by the way, maybe they're not useful for downstream application. I'm just saying that out there. That's not the purpose here, is to be a little bit more physically accurate, right? Not necessarily cater better downstream application. I think science has enough room for that as well. And so here on the right, I'm showing like the single return of a LiDAR scan. I'm showing where there were 2 returns. In blue is like where the range of the first return out of the 2 hit, and in orange where the second return out of the 2 hit. I want to be able to reproduce such maps. Okay, so what I argue is that these effects are mainly governed by 2 LiDAR principles. One is the fact that the beam is diverged, so it's not an ideal ray that is shot into the scene. And the other is that there's some intensity involved here. So it's important to know how much intensity came back, because the LiDAR is going to threshold that in some sense. So the first case of just returning a single range, can usually be modeled by the fact that you shot energy, it hit one surface out of maybe many, and that entire energy was absorbed or was returned from that surface back to your sensor with enough energy to surpass the threshold. That could explain a single return. Secondary returns mostly happen when some energy residual is left that's enough to hit a surface that's further away and still return enough energy to surpass the threshold, and then it manifests itself as an additional range in the measurement. Now remember that here we don't assume to have access to the raw raw time measurements of the LiDAR intensity. So we assume we're trying to do this kind of inverse problem of just looking at the hits or the ranges that were determined by the LiDAR as detections, and recover from them what's actually happening. The modeling here is in a way kind of a difficult inverse problem. Dropped rays, which I haven't mentioned here. It's hard to draw dropped rays because they're not there. But dropped rays are the case where not enough energy was returned. So maybe just residuals of energy hit some stuff, but in the end, it wasn't enough to pass the threshold. So it's either that there was a surface, but it didn't return enough energy, or there was no surface at all. That could also be an explanation. Okay, so back to the first question. How do we model the scene, and how do we model the sensing or the interaction between the sensor and the scene to achieve these phenomena that I was just describing? So first part, we're gonna borrow mostly from NERF, and we're gonna say this is still gonna be a volumetric representation. Only we don't care about colors now. We care about reflectance. And reflectance is the property is gonna tell us how much energy that hit a surface is gonna reflect back to our sensor. Plus features, we'll talk about that in a second. No one uses just like plain physics is not gonna fly here, unfortunately. Maybe if we have access to the raw measurements. Okay, how do we model the sensing? So I think the main point to say here is that now we're different from NERF. We're talking about active sensing. Active sensing, namely, we are the sensor, or the sensor is both in charge of shooting the energy and receiving the energy. Okay, so in that sense, one important principle to account for is that the two-way travel that the ray travels. So this is kind of manifested by some response function. So first of all, the pulse itself is not finite. It's going to travel and have some response function with the scene at some distance. So this is kind of the continuous convolution way of representing this. When we discretize this into chunks, we've kind of absorbed a bunch of sensor properties into the C coefficient. But what we see here is the two-way travel is manifested in the square of the transmittance. There's the density and reflectance from hitting the surface, assuming a Lambertian surface here in this equation, but later on we just replace it with a mapping of the direction of the ray. This is the cosine function here, and this is the range, right? We're going to have a decay of intensity as the ray is returned back to the sensor and diverge. So really, a key contribution here, I'd say, is the two-way volume rendering equation that we've devised here. So, just to convince you, so another element here, aside for the, this is taking accounting for the two-way ray traversal. The other one is the beam divergence. As I told you, this is a demonstration in a simulator. So we have ground truth. We have ground truth depth here. We kind of build a small simulator here, and we show that if you discretize the rays and if you use a diverged beam, so not just one ideal beam, you'd actually get a lot of errors, all along the scene in your measurements, and they're going to be more exaggerated towards like further away distances. So this is to convince you that what the LiDAR actually measures, if we don't account for beam divergence, we're going to lose all the ability to model these underlying errors. Okay. In practice, what the way we actually tackle this is, again, using this volumetric representation and sending the two-way volume rendering procedure. There's a little bit more to do. So in order to reconstruct that first phenomenon, the phenomenon that I was saying, we're going to first do a coarse volumetric rendering. We're going to do a peak detection. And then using that peak detection, we're going to just zoom in on that region, and we're going to recompute the densities along that region. It's important also for supervision. We don't want to propagate densities elsewhere in the scene to explain, the transitions between the measured distance and the actual distance. So we're gonna focus on a window. We're gonna kind of zoom in and gonna recompute the weights to get a refined range. Now, if we identify there's more than one return, which we do, remember those features that I mentioned earlier. These are going to help us when we shoot a ray to determine whether or not there is a second return. If we determine that there's going to be a second return, we're going to bring this back to a more principled fashion and truncate and have another volume rendering that starts at the end of the first one. So we take like the furthest we discretize the beam into multiple rays, we compute like the furthest distance out of those, and we start another volume rendering from that point on. Sorry, the minimum out of the discretized rays, and we're going to start another volume rendering from that point on to get the second return computed. And now to handle dropped rays, we again leverage this idea of using these additional features, and we have what we call like ray features, right? We integrate those ray features, and we can supervise them with dropped and heat rays that we can just get from the LiDAR scans, right? Anywhere we know the scanning pattern, so anywhere we didn't get a return, we can supervise this we can solve it like train it as a binary classification problem. So we can integrate the ray features, train them to tell us where we're not going to see any returns from the rays. This is how we can achieve this property of ray drops. So just to kind of hopefully convince you that this direct or more task-aware sort of solution achieves more physically accurate properties than the two-stage solution. Here we're showing all the different ray properties. So of course there's the first range estimate that gets improved. And this is a comparison, by the way, when we say ours here, there's like a few variations. We can use either a central ray, which is this ideal ray that doesn't diverge. We have the diverged beam, and we have the ground truth mask. So remember, we estimate where the mask is going to have a second return. We can also like use some kind of an oracle where we assume to, we just want to see how close we are to the oracle solution of, someone telling us where exactly is going to be two returns. So these are the different properties. On the second range, we can say we can see like how we see like a big improvement, sorry, on how well we can estimate the second range. This is where we really, I think, excel in this approach. And then this shows again this improvement in our ability to predict where it's going to be a first and second returns in the scene. So we're much closer to the actual returns. This is with respect to intensity, we can show here that we're again respecting more faithfully the intensity of the scene than previous solution. This is colored by in red. Here, for measuring accuracy of the actual returns, we actually devised a cool little, I don't know why it's not used more, but we devised like a cool, maybe you guys know about this, but we tried to say this is novel view synthesis, right, on real data. So we don't have a way to simulate. So we have two ways, right, to use real data. We can do interpolatory generalization, right? Basically, I don't know, drop out some views along the trajectory and try to see how well we can reconstruct them in those views, which is okay, but doesn't really generalize. What we did differently is we drove one trajectory, we learned the function, then we did a novel view synthesis of a trajectory that's 1.5 meters to the left, and then we used those as ground truth. So we again repeated the same exercise. So now we learned from our generated novel view synthesis, and we shifted 1.5 meters back to the right. And now we can actually do the closed loop testing and measure it against the original trajectory. And I just think this kind of closed loop testing or benchmarking is kind of a cool trick. I don't think I've seen that elsewhere, but happy to hear if it's otherwise. I think we should use it more. That gives us a way to actually use real data to evaluate how well we do. So this is the errors. Again, less red colors means that we're and less blue colors mean that we're more accurate. Yeah, let me just show you a bunch of, oh yeah, of course, to evaluate this on not just how accurate we are or how well we respect the original point cloud, the recorded point clouds, we also tested this on downstream segmentation and registration. So here we highlight a few places where we're able to recover a better segmentation map than previous solutions. And these are all kinds of different manipulations we can do. So I think I've hinted to all of them already. We can change the configuration of the sensor, we can tilt it, we can move it around. And we can like densify the beams or sparsify the beams, increase the beam divergence and whatnot. So just a few examples of shifting and lifting the sensor. And densifying the sensor here. On the left, there's the original trajectory. On the right, it's the densified version using more beams. Yeah, this is where we narrow down the divergence of the beam. Yeah, so to summarize, in today, really packed a lot of information about neural simulations, so how we drive scenes, take that data, and then use them to achieve more scalable solution, more sensor realism, and also motion modeling. And the emphasis in all of this is manipulation, controllability, anything we can do to make this more into a simulator and less into a replay. So we achieve this in a data-driven fashion. And so future directions, so stuff that I haven't discussed as much, and I think the question that came up was exactly hinting towards that. We need more semantic in here. We need more dynamic. So I haven't touched a lot on how we actually do dynamic, except for the motion modeling. How do we recover from dynamic scenes directly? And then scene editing, kind of like this is like a quick demo that we had internally on how to just remove some stuff from a reconstructed scene. And I think that's important, this editing of scenes I haven't discussed at all. And of course, more and more generative models to get us better assets and better scenes. So not just at the object level, why not just generate the entire scene? Why do we even have to drive it again? Yeah, quick announcement. I'll just use this kind of platform to say that, I'm very, as you saw in all of those works, we collaborate, or most of them, we collaborate with academic partners. So if you're interested in those topics, really feel free to reach out in one form or another. We'd be very happy to collaborate and work with you. Personally, I'm also looking for PhD students and postdocs. I'm recruiting. If you liked Israel, if you were there in ECCV, you should come or visit. There's also room for visits. We're going to have a SIGGRAPH course. So with Svinat here and James, we're going to have a course. So if you're interested in neural fields, I think you can take this 3-hour course and educate yourself, or just let people know about this. And then I also want to mention that I'm very interested in perception tests. I haven't touched on those much today, but we have a few works coming out on doing perception, on instant segmentation in indoor scenes. We have one work that just about doing this in an unsupervised fashion, and this monocular reconstruction from images using image cues to transfer them to the 3D scene understanding. And we're going to also have an ICCV workshop about open vocabulary 3D scene understanding. So if you're interested in that, join in, please. And that's our reading list. I'm going to just send the slide deck, so everyone who were interested in one of the papers here, just you'll have a link to immediately get there. And that's it. With that, 3 minutes behind.
Okay.